Hello, Integrated Math 1. Welcome to Module 1, Topic 2, Lesson number 4. Oh, we're nearing the end of our unit. I know we are so sad. So we are looking at how to take real world problem situations and turn them into mathematical sequences and equations and stuff that we can use. So you just did the getting started activity where you were moving around your 3 discs, either coins or if you cut out the discs from the back, but you were moving them around and stacking them up and seeing how few moves it would take for you to make a new stack. And again, the rule was that you couldn't put a bigger coin or disc on top of a smaller one. So you've already been playing with that a little bit, and you've already been looking for a pattern, which was the very first step, right? That was the very first step that we did. So the second step that we're going to do in our modeling process is to organize our information so that we can represent it using math, right? Using mathematical notation, some kind of formula or equation, right? Something like that. So considering that question from our getting started activity, the pattern, we were looking for a pattern and playing with that. Is there a relationship between the number of discs and the minimum number of moves? So to help us do this, to help us figure this out, we're going to make a table, okay? So go ahead and keep playing the game a little bit, but play the game with 1 disc. What's the minimum number of moves it would take to win? Play the game with 2 discs. What's the minimum number of moves it would take to win? And you were already playing with 3 discs, but play with 3 discs again. See what the minimum number of moves is it would take for you to win. So go ahead and hit pause, play with it a little bit and fill in this much of our table, and then hit play when you're ready to continue the discussion. All right. All right. So I played around with this. I did play with my lovely little discs and realized that that if I have 1 disc, I can win in 1 move. Yeah, that was pretty straightforward. 1 disc, move it, I won. Hey. For 2 discs, the minimum number of moves I could make was 3 moves because I had to move the little one, move the big one, and then put the little one back on top of it. So it did take me 3 moves to win with 2 discs. For 3 discs, the minimum I could do was 7 moves. I had to take the little one and move it, take the middle one and move it, put the little one on the middle one, move the big one. Like I took a couple of moves there. I got there, but it took a couple of moves. So it took me 7 moves at least in order to win with 3 discs. So this is what I got so far, just playing around with my discs in my games. Now, we're going to set our discs aside and for just a bit here, and we're going to see if we can find some kind of a pattern. Do you notice a pattern in your results? Is there a pattern happening here in your results? Go ahead and hit pause, jot down your thoughts on that, and then hit play when you're ready to keep the discussion going. All right, so there are a few ways of looking at this. I was like, well, I added 2 and then added 4. Maybe for the next one, I would need to add 6 and then add 8. Maybe that was the pattern you noticed. I noticed something that was really interesting. I noticed that if I doubled the number of moves right before and added 1, I would get there. So double 1, that's 2, plus 1 is 3. Double 3 is 6, plus 1 is 7. So that's the pattern I noticed. Again, you may have seen it a little differently. But I noticed if I look at the number of moves right before, I could double it and add 1 to get the next number of moves. So now that we see this pattern, you know what I'm going to ask you to do. Now that you see the pattern, let's see if we can make some mathematical notation to help us do that. So if I want to know how many discs it's going to take, the minimum number of moves for how many discs, I'm going to use a D for disc, and I'm going to say D sub n for number of discs. And that means then if I want d sub n, we said I would need the one before, which if you recall from your recursive formula training, the one before would be d sub n minus 1. That's the one before. And I had to multiply it by 2 and add 1. That's what we said. We said double it and add 1. So that's what I've got going up here. Wonderful. So here's the next step of our modeling process then. So we discovered a pattern. We've organized our information. We discovered a pattern, organized our information. We're starting to get into the mathematical notation. So our next step is to extend the pattern and start making predictions with our results. I know you're not surprised by this next step because you already saw this with our table. Yeah, I want you to extend the results. I want you to finish the table. Now knowing what we know about doubling it and then adding 1, then you should be able to find the next couple of terms, right? So go ahead and hit pause, find those next few terms, and then hit play when you're ready to check your work. Alrighty then. So this means if I keep going, so if I double 7, that would give me 14 plus 1 is 15. If I double 15, that's 30 plus 1 gives me 31. And if you need to use a calculator, it's cool. I get it. No judgments here. Calculators are a good thing. Let's just be honest about that. Yeah, so that seemed to be super helpful. And this may look familiar. Write a recursive formula. I think we maybe already did. So write a recursive formula to represent this pattern in our table. You may already know it because we kind of already did it. So go ahead and hit pause, write down your recursive formula, and then hit play when you're ready to check your work. Yeah, so our recursive formula is just the formula we wrote down earlier. We said if d sub n is the term I'm looking for, then d sub n minus 1 would be the term right before it. And we said to double it and then add 1. Boom, recursive formula, there it is. Yeah. And of course, if you wanted to, you could double check, you could plug things in and double check all that stuff. So if I want term 5, I'd have to plug in term 4, double it, and then add 1. Yay. Ooh, here's where it gets tricky. This one's trickier. This one's trickier. We now want an explicit formula because that recursive formula that we wrote was really, really great, but only if I know the term right before it. If I asked you for like, what if there were 30 disks? Oh my gosh, suddenly it's really, really hard, right? Suddenly that lovely recursive formula means I'm gonna have to make a really big table, and I don't wanna do that. So explicit formulas are great. So let's see if you can think of an explicit formula that would work. This one's trickier. I totally get it. Take a stab at it. You got nothing to lose by trying, and it's okay if you mess up. That's why pencils have erasers. So go ahead and hit pause to try it out and hit play, and we'll keep the discussion going. All right, so it took me a while to find the explicit formula. I'm not gonna lie, it did not just happen. I had to put some work into that mess. So I realized that 2 to the 1 power is 2 minus 1 would be 1. Ooh. 2 to the 3rd power, or pardon me, 2 squared would be 4 minus 1 is 3. 2 cubed is 8 minus 1 is 7. 2 to the 4th power is 16 minus 1 is 15. 2 to the 5th power is 32. Whoa, I didn't think about that. Minus 1 gives me 31. Yeah, it turns out this is an exponential equation. So if I do 2 to the n power and subtract 1, that will give me my minimum number of moves for my disks. So if I wanted to know, say, 10 disks, d sub 10, then I would grab my calculator, and I would do 2 to the 10th power and then subtract 1. So 2 to the 10th power and then subtract 1, which tells me that if I had 10 disks, it would take a minimum of 1,023 moves to win. And this is why I'm not playing with 10 disks. I feel like I have better things to do with my time. All right, then. So here's the deal. The final step of our modeling process is to interpret our results and to test our mathematical predictions in the real world. If your predictions are incorrect, you can revisit your mathematical work and make adjustments, or maybe even start all over again. So here's what you're going to do. You are going to construct a graph to represent your explicit formula. And it's actually pretty easy to do because you already have a table. Yeah, you already have a table where you have the number of disks and the minimum number of moves. Think of that as your independent and dependent quantities, as your x-axis and your y-axis. And go ahead and make a lovely little graph. So hit pause, use that table to make a graph for your explicit formula, and then hit play when you're ready to check your work. Well, I know my independent variable quantity was my number of disks, because I could play with however many disks I want to play with. But my dependent quantity was the number of moves, minimum number of moves required, because that depends on how many disks I'm using. So I made my x-axis my number of disks, and I made my y-axis my minimum number of moves. And then I just plotted the points. So here we had, what was that, 1, 1. Then we had 2, 3. Then we had 3, 7. And 4, 15, and then for 5 moves, how many do we have? We had a whole bunch. I don't have my table in front of me. But yeah, you get the idea. So I just plotted the points. Now here's what's interesting is it's very much an exponential equation, isn't it? You can see it's doing that curve. Not only was my variable in the exponent on my explicit formula, but it's making a curve, most definitely. Now, I have a challenge for you. Are you ready for a challenge? Oh yeah, bring it on. So suppose you could make 1 move every second. You're fast, you're good. How long would it take to complete a game with 25 discs? You're going to need to show your work on this. So go ahead and hit pause. You're going to want to use that explicit formula. Start with that explicit formula. So start with your explicit formula. Work out how long it would take with 25 discs. How many moves it would take, I suppose. And then see if you can figure out how long it would take you if you did 1 move per second. Hit pause to work it out. Hit play when you're ready to check your work. All right, so I started with my explicit formula. Seemed a good place to start. We said we had 25 discs, so everywhere I saw an N, I plugged in 25. And then I grabbed my calculator because there was no way. Remember how you can use the special magic button to do exponents on your calculator? It's a wonderful button. So I used my special button and I did my exponents first. And so 2 to the 25th power is 33,554,432. Yeah. Subtract 1. And that means that for 25 discs, the minimum number of moves to win would be 33,554,431. That's a bit much. That's a bit much. So, yeah, that's a lot of moves. So how long would it take you then if you did 1 move every second? Well, it'd be 33,554,431 seconds. Or if you divided that by 60, because there's 60 seconds in a minute, you would find out that it takes 559,240.533333 forever minutes. Or since there's 60 minutes in an hour, if you divided by 60, that would give you 9,320.675 hours. Or if I wanted to know how many days, it's 24 hours in a day. So I divide it by 24. And I find out that it's about 388 days. Oh, no, that's awful, isn't it? And that would be 388 days of no sleep. That's over a year. And you wouldn't sleep. And for what? To move discs. See, this is why I don't play with 25 discs, right? This is why I keep it simple. Let's stick to 3. I can handle 3. I feel better with 3 or 4, maybe 5. Yeah, otherwise that's a long time to be playing. And you got better stuff to do than play silly games all day. Come on now. So you can see that in this lesson, we were using a modeling process to figure out whether the number of moves in our disc game is related to the number of discs. And there was definitely a relationship there. So in the next page here, I just have the basic steps of this mathematical modeling process summarized in a lovely diagram. The whole point of math is to teach us to be problem solvers. It's not to memorize formulas. It's, do you know how to solve a problem? That's a huge thing that we're trying to teach you in math. And you'll notice it kind of bleeds over into the scientific method a little bit, right? You come up with a hypothesis, you test your hypothesis, you make adjustments based on it, right? That's what we do. It's what we do in math as well. You start off just by noticing something. You're like, I wonder what's going on there. And then you kind of organize that information a little bit, right? You kind of like, okay, well, I'll make a table, I'll organize my info. And then you use that to turn it into some kind of math that you can work with. You then use that math to kind of predict what's going to happen next. And then you test it. And if it works, great. Then you're ready to report it. If you're like, ooh, I tested it and that didn't quite work, then you go back to your organizing and mathematizing your stuff in order to keep going and working through it until you figure out what is actually happening here. So it's super important to have this modeling process down. Now, I want to point out something else as well. So this sequence was odd, right? It was a little weird because we're used to having sequences. We've been dealing with sequences that were either arithmetic or geometric. And this sequence kind of did both, didn't it? Because we had multiplication, right, that times 2, but we also were subtracting 1. So it was weird, right? Because it had both things going on, both things happening. But generally speaking, you know that when you do when you do arithmetic, it's add or subtract a constant. When you do geometric, it's multiply or divide a constant. And so hopefully you noticed with these graphs that when it's arithmetic, you just get a line, right? Your explicit formula is linear, and when we graph them, we just got lines. Whereas when you did your geometric stuff, because it was multiply or divide, it meant that we got a curve on our line. And in fact, when we wrote our explicit formula for our geometric sequences, they were exponential. Did you catch that? That there was an exponential curve going on, that our variable was in the exponent? Did you see that? I hope you did. As always, guys, I hope you found this helpful and I hope you found this useful. If you got questions or concerns, feel free to email me, pop in during office hours, or ask me questions during class. It's why I'm hanging out around this place. And I'll see you soon. Bye.